Hello Lana, how are you doing today? I hope you are okay. I hope the Lord has kept you going. I'm glad to join you once again on the same program of Knowledge Quest on Hope Channel Kenya. So welcome and join me once again for today's lesson, and let us learn together as you prepare for the examinations ahead of you. As you sit down and study, let us learn this one together. It will be good for your revision. So our subject again today is physics. I'm your teacher Peterson Maranga. I'm going to take you through Form 4 physics, and today we are going to proceed from where we stopped in our previous lesson last week. In our last lesson we were discussing about the mains electricity, and we saw how the power is transmitted from the power stations until it gets to our homes. We also looked at a few examples of the sources of the mains electricity. We talked about the geothermal power stations, the windmill generating plants. We talked of the hydroelectric power stations and many more. So we gave examples of the sources of the mains electricity. Today we are going to start from that point when the electricity has come to our homestead. It is right next to our house. So what do we do with it? So welcome, and let us start this together. So we are still in the same topic, mains electricity, and particularly now today we talk about the domestic wiring. When we were talking about the national grid, we said that the national grid had an input and an exit. In the input we had what is coming from the power stations, what is generated, 11 kilovolts, and then it is stepped up to around 400 kilovolts, fed into the national grid system, transferred through the overhead cables mounted on the pylons, and then to we had the local substations where there was a step down, and then we had substations for distribution. Now it has come to the transformers outside the houses. Now from the transformers outside the houses, the power is going to be drawn to our homes, to our houses. What follows after it has been drawn to our houses is the domestic wiring. So let us look at what domestic wiring is. Now generally from the local transformer, the power is supplied to our houses by two cables. There is a two-wire cable, and one of the cables is a live wire, and then the other cable is a neutral wire. So from the overhead, the last transformers before the houses, the power comes in two cables, one which is a live wire and the other one which is a neutral wire. So all through beyond here, where we write L capital, we are referring to a live wire. Where we write N capital, we are referring to the neutral wire, because we're going to use them repeatedly on the drawings, and so we cannot keep writing the live and the neutral all through. So there are three cables which are involved in many cases. So we have the live wire, we have the neutral wire, and at times we have another one which we call the earth wire. But for now, what is coming from the overhead cables after the last transformer to our houses is supplied in two cables, a live wire and an earth wire. The live wire is what carries the potential difference. We said that the last transformer reduces the power to what is convenient for most of the appliances we use in the house. In the house we use the TVs, we use the radios, we charge our phones, we have the fridges, we have the electric iron boxes, all those things we use in the houses. Most of them use electricity at around 240 V. Now that potential difference is applied on the live wire. So the live wire is the one which is having the potential of the 240 V. The other wire, the neutral, is at a zero potential. So it doesn't have the potential difference. Its work is just to complete the circuit so that the current can flow through. Remember, current flows through a circuit which is complete. When the circuit is open or incomplete, the potential does not flow through. So the neutral wire is there to complete the circuit so that the power gets into the appliance and then it comes out of the appliance through the neutral wire. So the neutral is to maintain a zero potential, and that is called the earth wire. So after it has come to the supply has come to the house, and then we have another third wire which is earthed, and it's at a zero potential. We call it the earth wire. The earth wire will be represented by E. So E here represents the earthing. L is the live wire, the one which is having as a potential, and then we have N which does not have. Now the power is passed once it comes to our houses. The first thing that happens is that it is passed through a main fuse. So the main fuse is fitted on a live wire. This is very important for you or for us. So once the power is drawn through the two wire cable from the overhead cables, it is first passed through the main fuse which is fitted on a live wire. And remember, we have already said that the live wire is the one which carries the potential difference. So the earth and the live wire and the neutral wire do not have the potential, and so we fit the main fuse on the live wire. Now after the main fuse, the power goes through the joule meter, and sometimes known as the supply meter. This is where the consumption, whatever is used in that homestead, is going to be recorded for the purpose of billing. You know, we need to pay for the electricity, we need to pay for the consumption, and so the meter is what registers what has been consumed, so that we pay what we have, we pay for the consumption that we have during the period in our houses. So first the power passes through the main fuse, it gets into the joule meter. The main fuse is used for protection. If the power goes beyond what is required in the homestead, the fuse will cut off the supply so that it doesn't even get to the meter. The meter records, it registers the consumption within the household. Then we have after the meter, the power goes through the main switch. So we have these main components. So the power gets to the house through the main fuse to the joule meter. After the joule meter, we have the main switch. After the main switch, now the power gets into something else known as the consumer's box, or sometimes known as the fuse box. This is the point where the various circuits are going to be coming from. So the consumer box gives the distribution of power to different circuits within the house. Probably we have the lighting circuit, we have the ring main circuit, we have the heater circuit, we have the cooker circuit. We can have different circuits in the house, and all of them are generated from the consumer's fuse box. The difference is that the requirement of the heating circuit is very different from the requirement in the lighting circuit. Bulbs require much less current compared to the heaters and the cookers, and so they cannot be connected in the same circuit, because if they're in the same circuit, a lot of current is going to flow through, which may make the bulbs to blow off. And so because of that, we ensure that the bulbs are in their own circuit, the heaters in their own, the cookers and the ring main for the purpose of charging the phones and connecting the fridges and the TVs and what have you. So those ones originate from the consumer's box, or we call it the fuse box at times. There are different circuits, have different fuses. That is why sometimes the name is called the fuse box. So these are the important main parts of the domestic wiring. So the main fuse, the joule meter. From the joule meter, we have the main switch. Now the main switch is used so that should you want to cut off the supply of the electricity to all the circuits in the house, you don't have to go switching independently. You go switch off the lights, you go switch off the ring main, you go switch off the cooker, the heater. The main switch cuts off the supply to all the circuits within that house. But of course, once you have the lighting circuit, it has also its own switch controlling all the bulbs in the house and the rest of the circuits we have. So the main switch cuts off the supply to all the circuits. This is useful the moment maybe you want to do a repair within the house. You need to ensure there is no electricity to avoid the risk of electrocution. So we make use of the main switch to cut off the supply to all the circuits within the house. Now the power that is coming through the live and the neutral wire from the overhead supply is usually at a potential of about 240 V, and at an AC current which is at a frequency of 50 Hz. So this information is also important to you. That is why now when we are talking about the power distribution, the transmission from the power plant to the consumer, the power was generated at around 12 kilovolts, stepped up to 240, and then in the process, by the time it gets to the house, it is stepped down to about 240 V, and because it's an AC, it is alternating at a current of, at a frequency of approximately 50 Hz. So once once we're in the house now, something is going to happen. But before we get there, let's look at a recap of the functions of the various parts we have mentioned. We have talked of the main fuse. The main fuse where the power first gets into. So you see the two cables first pass through the main fuse. The main fuse is used to cut off the supply in case of power upsurge, in case of a fault in the house. So the main fuse blows off, and so there is no power which is coming off. So it cuts off the supply. This is only in the case of a fault. So it is to protect you, to protect the house and maybe the building from excess power that can cause damage in the form of fire or something else. So it cuts off the supply should there be a fault. Now, after the main fuse, we have a joule meter which measures the energy consumed. So it measures and registers, it records the consumption within that house. Then we have the main switch. The main switch also cuts off the supply, but only when we are doing a repair or when we want to do something in the circuits within the house. The fuse cuts off the supply when there is a problem or a fault. The main switch cuts off the supply when we want to do a repair, when you are the one deciding to switch off. And then we have a consumer box or the fuse box. This one houses the different consumer units. That is the purpose of the consumer fuse box. It is to house the different consumer units. The different units or circuits you can have in the house include the lighting circuit. We have the ring main circuit, the heater circuit, the cooker circuit, and there could be other circuits. So all these circuits, all these units must originate. They start from the fuse box and they end there. So we have the live wire and the neutral wire drawn all the way from the fuse box and also coming back to the same point. And so we realize that each consumer unit, that is the lighting unit, the lighting circuit, the ring main circuit, the heater circuit, each one of them is connected to the fuse box through a fuse. So each one of them has got its own fuse, different from the other circuits. And actually, the fuse ratings will be very different for the different circuits. It's because of different current requirements for the different appliances. For example, the current required by an iron box is not the same as the current required by a bulb in the house, and so they cannot be connected in the same circuit. Therefore, each of these units is linked to the fuse box through a fuse, and this fuse purposely is used to cut off the supply if there is a problem with that particular system. So if there is a problem with the lighting circuit, this fuse can switch the lighting circuit off, but the other ones are still on. So this one ensures there is independency in terms of the supply to the different circuits, so that when there is a problem with the ring main circuit, it does not affect the lighting circuit. If there is a problem with the lighting circuit, it doesn't affect the cooker circuit. So each one of them has got its own fuse, which is linking it to the fuse box. So we can have this flow chart to summarize everything that we have mentioned. So from the overhead cables, from the supply, we draw the power in terms of two cables. We have the live and the neutral. They get first through the main fuse, and the main fuse, we have said, is to cut off the supply if there is a problem in the house. If maybe the power increases beyond what is required, so it cuts off the supply. Then after the main switch, we have a meter, the joule meter, and the purpose of that one is to register the consumption, to record what is being consumed in that house. Then we have the main switch. This one is used to cut off the supply when we are doing a repair. You are the one who is switching off. There is no problem. You want to do something, and so you decide to switch off. So we do it at the main switch. After the main switch, we have the fuse box. The fuse box is going to give us room to come up with the different circuits. We can have the ring main. The ring main circuit is the one which leads us to the sockets where we can charge our phones. It is called the ring main circuit. Then we can have the lighting circuit, we can have the cooker circuit. All of them are connected independently to the fuse box and through a fuse, whereby again we have said that those fuses are to cut off the supply if there is a problem with that particular circuit. So if there is a problem with the ring main circuit, the fuse connecting it to the fuse box will blow, and so the ring main circuit will go off. There will be no power. If there is a problem with the lighting circuit, that fuse blows off, it cuts off the supply, there will be no light in the house because there is no power getting there. The same thing to the cooker circuit. So in a nutshell, then that's how the power comes in. But much as we mentioned the live and the neutral wire, there's something else that we said. Earthing is done. Earthing is done at the moment the power is drawn to the house. Because when we talk of the ring main circuit, the ring main circuit has got three terminals. There is an earth terminal, a live terminal, and a neutral terminal. So the earthing is done at the homestead, whereby one cable is connected to the ground, and so the ground keeps that terminal at zero potential. It doesn't have any potential difference, and its purpose is for safety purposes. It's just to protect the user of the various appliances. So this is what we have now when it comes to the domestic wiring. We have come from the power supply. The power has come through the neutral and the live cable, and so it has come first through the main fuse. So after the main fuse, which we call it the board's main fuse, it gets to the meter. Then after the meter, we have a main switch down here, which leads to the consumer unit. So these are the things that we have given in this flowchart. So we have the power supply, the main fuse, the meter, the main switch, the fuse box, the different circuits. So this is what we are having here, and you realize that we are using some specific colors. I'll just show something before we go back there to that diagram. In domestic wiring, we have something called color coding. We have different wires to connect, and to avoid confusion, we have specific colors used for different cables. So the conventional colors used are red or brown is used for a live wire. So if you see this cable here, it's always connected to the live terminal, and then blue or black is used for a neutral wire. So this blue, this cable is always connected to a neutral, or we call it a neutral wire. Then green or yellow, or green with yellow strips, it is used for the earth wire. So these are conventional colors. So blue or black, that is neutral wire. Red or brown, that's a live wire. Green having strips of yellow, green or yellow or with strips, then we talk of an earth wire. So with that, we can just go back to this diagram. So you see that we have a black here. So that tells us that this black color, or that black color, is the neutral wire. And then the red on the other side is a live wire. So where you see a red anywhere here, that is a live wire. Where you see black, that is a neutral wire. Or we can use a blue for the neutral wire. So we can follow it again so that we have some understanding of what is happening here. So the power has come from the power supply. We have a neutral, we have a live. So the live wire is the one which is passed through the fuse. Usually the fuse is installed on the live wire. Fuses are not put on the neutral wire. Again, we mentioned that the live wire is the one which carries the potential. So there's no potential on the neutral wire, and so there's no fuse there. So we have a fuse here. The two proceed together to the meter. Now past the meter, we have changed the color for the two cables. Still, now we have brown and blue. Brown is the live wire, and the blue is the neutral wire. So they pass through the main switch. So we have a switch here, and the main switch now is connected to both the live and the neutral. And what happens, we said the main switch is used to cut off the supply if there is a repair that is to be done in that house or in that connection. So after this one, we go to the distribution box consumers unit inside here. So from here, we have the neutral wire, the blue one goes, and then we have the live wire. Actually, now we call it the neutral bus bar, and the other one is called the live bus bar. So what is happening, for each of the circuits we're going to have in this house, they must have one terminal connected to the live bus bar and another one connected to the neutral bus bar. So let's first quickly see through the lighting circuit that we are having here on the left. This has a cable connected to the neutral bus bar, the blue bus bar on top there, and then we have another one connected to the live bus bar down here. So we have the neutral and the live, and so the cable connected to the live bus bar is connected through a fuse, and the purpose of the fuse we already mentioned it. So we have a complete circuit here for the lighting system. And then if we consider another circuit for the heater, it has one cable connected to the neutral bus bar on top and another one connected to the live bus bar. So it has a complete connection on its own. And then the live is connected through a fuse of 15 amperes. So the lighting is connected through a fuse of 5 amperes, meaning it cannot allow a maximum current of 5 amperes to flow through. For the heater, a maximum current of 15 amperes is allowed to pass through, so you can see that one. And then we have another ring main circuit. Ring main circuit is what we use for the sockets, to which we connect our fridges, radios, TVs, and all those appliances require different amounts of current. So the ring main circuit is connected also to the live bus bar through a fuse of rating of 30 amperes. That means a maximum current of 30 amperes can flow through. And then we have another one connected to the neutral bus bar. But in addition to this ring main circuit, we have the third terminal connected to the earth wire. It is now represented by by yellow and green. So we have the earth, we have the live and the neutral, all of them leading us to a socket. So this is where we have a socket, an example. So there is a live terminal, a neutral terminal, and an earth terminal. We have another socket with the same and another socket with the same. So the earth wire is to ensure protection of the user of the appliance if there is a fault. So that is what how the domestic wiring is done. The most important thing for us to have in mind is how the two cables from the overhead supply come in. We have the live and the neutral passed through the different stages until it gets to the particular appliance that we are having and we are going to use it for. So in this case, the appliance is the bulb. For this one, we have the heater. For this one, we have the cooker. And then for the sockets, it depends on what we want to connect there. But again, maybe importantly for you to know is that the earthing did not come from the main, from the supply cable, from the overhead cables. The earthing starts here. So earthing is done at the consumer's unit. That is where we have the neutral, one terminal connected to the ground. What happens is if there is a fault, the excess current is connected to the ground, the excess charges are connected to the ground, and so safeguarding the user. Say, for example, you are using an electric iron box and the metallic casing happens to be in contact with the other terminals. So the excess charges will be carried by the earth terminal to the ground, and so it safeguards you. So that is what we have concerning the domestic wiring and the color coding. So when we come back from the break, we're going to look at more information concerning the costing of the electricity. So we're going to have our short break. Do not go away, stay tuned. Let's meet after the break. Dear learner, welcome back from the break. Let's proceed with our discussion. Before we were discussing about the domestic wiring, how the power is drawn from the overhead cables through two cables, the live and the neutral, until it gets to the particular appliance that we are going to use. So we realized that there are a number of things which happen there, but most importantly is that when we are going to do a connection, we maintain a similar color for a given terminal. So if it is a live wire, we are going to have red or brown. If it is a neutral wire, we're going to have a blue or black. If we are to have green or yellow, it means that is the earth terminal. So that when we're doing the connections, if we want to come up with a new circuit in the house, you still go to the consumer unit, you check out where we have the live bus bar, which will be blue, which will be brown or red, and where we have the neutral bus bar, which will be blue or black. Then you fit your circuit there. So one terminal will have to lead to the neutral, the other terminal will have to lead to the live wire. And then depending on the kind of circuit you're coming up with, we can have the neutral, we can have the earth connection on the other side. And so that is what we were discussing before we had our short break. Now I want us to have a look at this one, the 3-pin plug. These are things that you are very familiar with. The chargers we use for our phones, the chargers for the computers and the laptops and other appliances, the iron boxes, the immersion heaters and other things we have make use of, they have this 3-pin plug. Now the purpose of a plug, whether it is a 3-pin plug or a 2 plug, is to connect the appliance to the socket. The appliance needs to a potential difference for it to function, and so the plug will connect the appliance to the socket from which it's going to draw the potential for it to be used. So the 3-pin plug, just like any other plug, connect the appliances to the socket. Differently from the 2-pin plug, a 3-pin plug has got 3 terminals. It has the live terminal, it has a neutral terminal, it also has an earth terminal. So this is what I'm talking about. So there is one terminal here, there is another one, and we have another one at the center there, and there are 3 number. That is why we call this a 3-pin plug. The fuse is connected to the live terminal. I think this is now a general thing that we need to have in mind. Wherever we're going to have a fuse, fuses are always fixed on the live terminal and not on any other terminal. A fuse is always fixed on the live terminal. So, and then we have the earthing pin on the other side. So before we get there, let's just look at what we are having. So when we open this plug inside, this is how the 3 cables are connected. We have one side the connected to the neutral, another one connected to the live, and then we have the earth up here. So remembering the color codes that we have just mentioned previously, so it means this black cable is a neutral, so we have a neutral terminal, and this red one is for the live, so we have the live terminal. And again, now you can see the fuse is put on the live. So that's why we're saying that the fuse is connected to the live, and then we have the earth on the other, the center. Of course, the color coding again tells us that that is the live because of the green and the yellow colors. Now, what we say for a 3-pin plug, it's very common for appliances whereby more current is going to be drawn through, and sometimes it gives us more protection because if there is a fault, the earth is going to connect the excess charges to the ground, and so you will be protected as you are using the appliance. But then the three pins on that plug are not of the same size. You realize that there are 2 shorter ones and one is longer. The earth pin, which is at the center, the earth pin is always at the center, so the longer one is longer than the live and the neutral pins, and the reason is to open the socket when you are plugging in. Usually when we have a socket, you realize that these 2 holes are always closed, and so if we are to use a 2-pin plug to plug in, you need an object for you to press here so that these holes are open for you to insert a 2-pin plug. But if we have a 3-pin plug, then the earth terminal, that pin is made longer so that when you are plugging in, it is able to open the live and the neutral pin holes for you to, it opens the holes for you to plug in into the socket. So that is what we are having. And usually because of the addition of this one, a 3-pin plug has got an earth terminal which is not present for the 2-pin plug. Let's take some time and some few minutes and look at what a fuse is. When we talk about a fuse, this thing which is mounted here on the live terminal or what we were talking about is used to come up with the different circuits. So there's a fuse here, there is a fuse, there is a fuse, there is a fuse. So what is this that we are calling a fuse? We said when the power comes from the mains supply, it is passed through a fuse. So what is this that we are calling a fuse? A fuse is a short wire of low melting point. What happens is that when current passing through exceeds the requirement or exceeds the rating, the fuse will melt, and in the process it cuts off the supply. So we say a fuse is a short length wire that melts when current exceeds the rating. So if this fuse for this particular plug is 3 amperes, so if the current goes beyond the 3 amperes, the fuse is going to blow, and if it blows, that means it melts. It will cut off the supply, so there'll be no connection from this plug to the particular appliance that you are using. So the fuse rating depends on the requirement of the appliance. So if it is a TV requires a particular current. Of course, different TVs require different currents. If you are using a home theater, or you're using something else, a woofer or subwoofer, all of them require different currents, and there's always a rating. So that fuse will protect that appliance from excess currents, because if the current exceeds what is required, it's going to melt. So that is why we're saying that the fuse is a thin, short wire which is melting when current exceeds a particular rating. And so these are the diagrams. These are pictures. These are pictures of a fuse that are common in the market. You can get it in the market. So these are fuses. And then from one, we gave these two as the symbols for the fuses. So if we're going to draw a fuse in a diagram, we not draw these two. This is a picture. So if we were to draw a fuse on a diagram, this is what we are likely to see. So that now if you check again what we are having, then it tells you that this is a fuse, this is another fuse inside there, this is a fuse, this is a fuse, this is a fuse. The rating of this fuse is 5 amperes, the rating of this one is 15, the rating of this one is 30, the rating of this other one is 30. So we have different fuse ratings, and as I have mentioned, that one depends on the particular appliance you are going to use. So we have this is inside this thing. That is how the fuse looks like. If it was put in a transparent glass, there is a very thin wire inside there. This is a terminal, and this is another terminal. So current has to pass from this terminal to the other one for it to continue flowing to the appliance. So if the current exceeds what is required and that wire melts, so there will be a gap between this terminal and the other terminal, meaning there is no current getting to the appliance. So what we have down here is an example of a blown out fuse. This one cannot be used because it has blown. You can see some gap from this part to that. So when the current exceeded what was required, the short length wire melts, and so there was no, it cannot be used. There will be no supply, so we cannot use it. So this is what we call a fuse. And at times we can use circuit breakers in place of the fuses. The difference is that a circuit breaker can be reset. They work the same way, but a circuit breaker can be reset once it has cut off the supply. But once the fuse blows, the only solution is to replace. So if this fuse gets blown out, the only solution you'll do is to throw it away. You get another one, you use it in its place. So once a fuse blows off, the only solution or the only remedy we have there is to replace it with a new one. But if we had a circuit breaker, what happens is that it's going to, it can be reset once it has cut off the supply. And then if we have a circuit breaker, it responds instantly to power upsurge. But for a fuse, it has to take a few minutes or some time for it to melt. So then a circuit breaker is a more effective way of controlling power upsurge in the for the appliances that we're going to use in the house. Now, having discussed all that, assuming the power has come, you have connected the different appliances. You have the ring main circuit, you have the lighting circuit, you have the cooker circuit, all the circuits in the house, and you have the appliances running. So how do you pay for the electricity that you have consumed? Because by the end of the day, we have to pay bills for what we have consumed. KPLC is going to charge us, and for them to charge, now let's look at how the costing is done. So the power company uses a unit called a kilowatt hour for them to do the costing. So the electricity we consume is measured in units known as the kilowatt hours. Usually this is the energy transformed by a kilowatt appliance in 1 hour. A kilowatt, this means 1000 watts. Kilo means 1000, and so watts are the units for power. So when we talk about kilowatt, we are referring to the energy transformed by a kilowatt appliance in 1 hour. So 1 kilowatt hour is equal to 1000 watts. Kilo means 1000. So when we talk of 1 kilo, that is 1000. So we have 1000 watts. And then in terms of hours, 1 hour is equal to 60 minutes, 1 minute is equal to 60 seconds. So the total amount of energy we are referring to when we talk of kilowatt hours, we have 1000 times 60 times 60, which is equivalent to 3,600,000 joules. So this 3.6 million joules. So that is just 1 unit. Meaning if the power company was to measure the power in terms of joules, it's going to be a very big value, which will be inconvenient for representation in the meter. And so to avoid that, the kilowatt is more convenient for measuring the units consumed in the house. So 1 kilowatt is equal to 3.6 million joules of electrical energy. So the meter used for measuring the electrical energy uses the kilowatt hours as the units. So these are the units you're going to see for the meter that you are going to use to register what is consumed. So this meter is known as the joule meter because ideally it is measuring energy, it is recording the energy consumed, and the SI unit of the energy is a joule. So sometimes it's called a joule meter. Now when it comes to costing, I just wanted to take us through the examples that we have, and it will help us understand how the costing of the electricity is done. We have an example here. An electric kettle rated 2.5 watts is and uses a voltage of 240 V. Let me repeat. An electric kettle is rated at 2500 watts and uses a voltage of 240 V. The first question: if electricity costs 1.1 Kenyan shillings per kilowatt hour, what is the cost of running that kettle for 6 hours? I'll just stop it there for now. So we want to pose the question to you. So we go to the solution part, and then we read the second part. So here we have an electric kettle. The rating is 2.5 kilowatts, and then it's operating on a 240 V supply. The cost per unit is 1.1, and then the kettle is allowed to run for 6 hours. So how much is going to be spent running that kettle for the 6 hours? So we have a solution here. There is that energy transformed in 6 hours. So the rating of the kettle is 2500. 2500 watts is the same as 2.5 kilowatts. For us to change from watts to kilowatts, what we do is we take the watts that we are having, you divide by 1000. So 2500 divided by 1000 will give us the 2.5. So the energy transformed in 6 hours will be 2.5 kilowatts. Now this is in terms of kilowatts, then times 6, it will give us 15 kilowatt hours. So this is the energy consumed or transformed in the 6 hours. Now if one unit is costing 1.1 Kenyan shillings, this kettle in 6 hours will have consumed or will have used 16 units. So 1 unit costs 1.1. What about 15 units? So the cost of running that kettle for 6 hours will be the number of units, which are 15, times the cost of 1 unit, which is 1.1. So the total cost after the 6 hours will be 16.5 Kenyan shillings. So that is how we calculate the cost that we're going to pay. This is direct from what we have consumed with that appliance. In the second part, it says, what will be its rate of dissipating energy if the mains voltage is dropped to 120 volts? Suppose the mains is no longer 240. It is actually reduced to half. They have the original value. So what do we have here? So for part B, we say from the definition of power, power is the square of the potential difference you divide by the resistance. So, but the power consumed is 2.5 or 2500 watts. So from here, it tells us that the resistance is equal to V squared divided by R. V is 240. So 240 squared divided by 2500 gives us the resistance is 23.04 ohms. So the resistance of the element of this kettle is 23.04 ohms. So the current dissipated will be equal to V over R. The V, when it's operating normally on the 240, current supplied will be 240 divided by 23.04. That gives us 10.42 amperes. So when this kettle is operating normally, the resistance is 23.04 and the current flowing through is 10.42 amperes. Now, if the potential difference is reduced to half, the power dissipated will be equal to V times I. Our V now is no longer 240. The new V is 120. So we have the V 120 times the current. You know, by the end of the day, if that kettle is going to operate, the current flowing must be 10.42 and not less than that value. So assuming the same current is flowing through, then the power dissipated will be equal to the potential difference 120 times the current. So we get 1250.4 watts. That will be the effect of reducing the power flowing through. So we have another example, example 2. An electric heater is made of a wire of resistance 100 watts ohms connected to a 240 V mains supply. Determine Roman 1, the power rating of the heater. 2, the current flowing in the circuit. 3, time taken for the heater to raise the temperature of 200 grams of water from 23 to 95 degrees Celsius, given the specific heat capacity of water is 4200. And then the cost of using the heater for 2 hours a day for 30 days if the power company charges 5 shillings per kilowatt hour. So here we have a case where we have the resistance is 100 ohms and the potential difference is 240 V. Now, power rating, power is given by V squared over R. V is 240, so 240 squared divided by 100 gives us 576. 240 squared is 57,600. 57,600 divided by 100 is 576 watts. So the power consumed or transformed is 576 watts. But now in terms of talking of the rating, the power rating is given as 576,240 V. This means that if that heater is operating on 240 V, it will be transforming 576 watts. So this is the power rating of that heater. Now part B asks us to get the current flowing in the circuit. So power is given by VI, meaning current is the power you divide by V. The power is 576, the V is 240. So 576 divided by V gives us 2.4 amperes. So the current flowing in that circuit becomes 2.4 amperes. And then the other question is we get the time taken for the heater to raise the temperature of 200 grams of water from 23 to 95, given the heat capacity, specific heat capacity of water is 4200. So here we use this expression. The heat from supplied by the heater is the heat gained by the water. Heat is the same as the electrical energy given by power times time. The heat gained by water is the mass of the water times the specific heat capacity of water times the change in temperature. So the power rating is 576 times the time, which we are looking for, should be equal to the mass of water. 200 grams is the same as 0.2 kgs. So 0.2 times 4200. 4200 is the specific heat capacity of water, and then times the change in temperature. The temperature is increasing from 23 to 95. 95 minus 23 gives us 72. So that is why we have a 72 here. So if you solve this expression, you get your T is 105 seconds. So it will take exactly 105 seconds for the temperature of this water to rise from 23 degrees Celsius to 95 degrees Celsius if that heater is connected there. Finally, we are looking for the cost. So the total cost will be equal to the number of kilowatt hours, the units consumed, times the cost per unit. This heater has a power rating of 576 watts. So that means the rating is 0.576 kilowatts, because changing from watts to kilowatts means we take that value divided by 1000. So this in terms of kilowatts is 0.576. So then we have the number of the kilowatts is 0.576 kilowatts. It is taking 2 hours a day, then it is used for 30 days. That is the information we are given. It is operating for 2 hours for 30 days. So then the total number of hours is 2 times 30, which is 6 hours. So in the solving part of it, we have the kilowatts 0.576 times 2 hours, then times the number of days. So this gives us the total number of hours, then times the number of the cost per unit, which is 5.0. So the total cost when you solve this gives us 172.80 Kenyan shillings. So that will be the cost of using that heater for that duration. That brings us to the end of the mains electricity. As a student, all you need to know is that how the electricity is transmitted from the power plant to where the consumer is. How the connection takes place from the consumer's distribution box to the appliance which is going to be used, and then after that finding or estimating the costing, the total bill you are going to expect at the end of the month. So usually the electricity is going to be charged depending on the number of units consumed, and the unit of measure here is in terms of the kilowatt hours, because if we were to measure the units, the energy in terms of joules, we'll get a very huge value which will be inconvenient for us to keep writing. And so to reduce it to a figure that you can easily comprehend and write, we have a kilowatt hour being used. So we're going to come up with another lesson where we're going to do more questions concerning the calculations on the costing of the electricity and answering some questions on how they come from the current electricity. So in our subsequent lesson, we are going to have a brief revision of the content that we have discussed in the series. So we're going to have a revision of the different topics, the modern physics and the mains electricity that we have discussed here, and the other topics that we have covered before. So as a student, I wish that you continue reading, working hard. If you have questions, probably in the future, we're going to take them and try to answer them. But for now, until we meet again next week, same place, same time, may God keep you safe. Thank you for watching me. Thank you for having joined me. Stay tuned. Do not go away. So let's meet next week, same place, same time. Otherwise, goodbye.